Hello, I'd like to welcome you to our December Fireside Chat for our experimental design course. This is the last Fireside Chat of 2021, but we're going to be back in 2022. We've got a pretty full slate of things organized for you. And I hope you enjoy doing these or watching these as much as I enjoy doing them. For those of you that are new to the course or to the Fireside Chat, this is something that we do monthly, typically with a guest speaker, and we talk about specific topics in design of experiments or some applications of the concepts. I really enjoy doing these. I tell people that I'm channeling Franklin D. Roosevelt, of course, who did Fireside Chats on a monthly basis from like 1933 to 1944. I'm not sure I'm going to be doing them for 11 years, but I enjoy it a lot, and we're going to keep doing them as long as people find them interesting. Typically, we always have time at the end of the guest presentation for some Q&A. And this is a great time for you to send in questions, and they can either be about the topic that the guest presented, or they could be about anything from the course, or it could be a question specific to a particular situation or problem or application of experimental design methodology that you're encountering. We record these Fireside Chats, and they get posted to our Coursera course. You'll find them in the resources tab of your design of experiments course on Coursera. Quick reminder about how we like to run these. Please continue to keep your microphones muted and your cameras off. That sort of avoids any sort of background noise or other kinds of things that make it difficult for people to hear. And if you want to send in a question, the best way to do that is with the chat function on the Zoom menu. And you don't need to wait until the Q&A session starts. You can submit your question anytime, at any point during the session, and please don't hesitate to do that. If we get questions that can't get answered during the broadcast, then don't worry about that. We'll respond to that in Coursera later on for those that are enrolled. And usually we do a pretty good job of getting those back in the program, in the course, pretty quickly. Our guest today is Dr. Jim Wisnowski. And Jim is co-founder and a principal consultant at a firm at Sergo LLC, and this firm specializes in training and consulting work in experimental design, a lot of different aspects of applied statistics and predictive analytics and reliability engineering. He's published pretty widely in this area, including articles on experimental design. He was a career Air Force officer. He retired after 20 years of service in the test and force structure analysis area. And he had a lot of leadership responsibilities as a squadron commander, a joint staff officer. He was also an Air Force Academy professor. He got his PhD at ASU, and he was my PhD student. And I'm very, very proud of Jim. He's had a super productive career, and he's going to give us a presentation today on some new methodology that he's been developing. And so, Jim, I'm gonna turn this over to you for the presentation, and looking forward to this.
Well, thank you very much, Doug. I appreciate the invite to join the Fireside Chat. And I guess today it is appropriate to have a fire, given it is approaching the winter. So the Fireside Chats in perhaps July and August aren't nearly as needed, right?
Well, it was a little chilly this morning. It was like 55 degrees when I was driving in, but I still had the roof down on my car.
Brutal.
Yeah. But the seat heater was on. I was fine.
You got the winter package. That was a clever move on your part. So speaking of drives, The way the future is going is we may have a lot of these cars that are driving by themselves, like the Teslas that we could call autonomous systems, not
Yep.
only cars, but in the Department of Defense, some of the aircraft, and even Amazon Prime using some autonomous systems to deliver your packages that you've ordered for holiday shopping.
Well, I just wanted to ask you something, because I saw an ad on television the other day, and there's this car driving across like this bridge, and it automatically changes lanes and passes another vehicle in front of it. And everybody's sitting in the car going, they're so happy. You know, it looks like this is a really good way to get killed. I don't know. I'm not sure how that works.
Yeah, for those that are in the world of autonomous systems, that is one of the big things, is the trust level, right?
Yeah.
Do you honestly believe that the system will be able to execute the right maneuvers? So it is quite scary. In fact, even you can summon your Tesla, right? So you're done your restaurant, it's raining out, so have it come from the parking lot and driving by itself.
Wow.
And that is scary for the parking lot attendants and people walking into the restaurant. So, so you got to have good software and believability and trust, and all that comes from testing, right? So, so even when we think about autonomous systems in terms of Mars rovers and things like that, we have to have an amazing amount of test and credibility in these. And as it turns out, the design of experiments is an important pathway in order for us to achieve not only the level of sophistication and complexity of the software, but also for us to do that rather efficiently. So this talk, we're going to kind of maybe take a little bit of a transition from thinking about physical systems in DOE, and then focus more on what happens in a software intensive environment where things change up just a bit. So we still are going to look at some of our foundational principles of DOE and the like, but our goal here is to really think about how, one, do we test these systems, and two, more importantly, is how do we come up with additional points once we have figured out some things we need to take that next step. And the fuel, if you will, to really learning and developing these autonomous systems are high fidelity simulations. So computer simulations are really how we learn the most about these. So, so with that, let's talk about DOE for computer experiments. So you're all very well familiar with the classic design of experiments, but here we may have a little bit of different scenario where we depart the physical system and we're in the software. And there's really two flavors of computer experiments, one being the Monte Carlo type, where you could think of the same inputs don't necessarily result in the same outputs. Different from that would be these ideas of deterministic. And this is a lot of engineers and physicists are using these models, finite element models, computational fluid dynamics, and they are characterized by very complex surfaces, but there is no random component in it. So the exact same inputs are going to lead you to the same output. And that's something that we can actually exploit. So there's no noise, so life is good. And given that, rather than what we'll call a space filling, or we'll call it a space filling rather than a factorial or fractional factorial design that our grandfather of design of experiments and has been so useful to us that we see on Doug's fireplace there, Sir Ronald Fisher, we kind of depart those ideas and maybe say, what happens if we can just kind of put a uniform spread of these points across the design space, which is maybe what some folks not well trained in DOE may think is an intuitive idea anyway. But we know why we want to use the factorial designs. But when we don't have any noise, these ideas come into play with space filling designs are pretty clever, actually. So the space filling design is going to be our best bet for us to accommodate some of the complexities. And I kind of stole a picture from Doug's textbook here, the 10th edition, I believe. And this is not uncommon where we're doing a finite element model here, and you can kind of see the mesh is going to be the level of granularity, if you will, of this component. So we can see that a linear approximation is probably not going to do us well. So we have to get a little bit more points. It's not just the high and low and maybe the center point. Well, we need some stuff in between. We found that hybrid designs work out pretty well for this, as well as sequential experimentation being highly applicable to this world. So this talk, we really have two goals here. The idea is to introduce two new designs that we're going to look at in terms of their applicability. Not only we'll use as a use case the autonomous systems, but they are scaled well to other applications. So the first thing we want to talk about is gap filling designs. So this is a space filling design, and we'll talk about what happens when I have gaps in my design. How do I do that? But more importantly, we want to say, given I have some data already, let me exploit that so that I get new points that help me on the areas of interest. So where the response surface is flat, I don't need additional points there. I need it where the action is, right? So you can kind of think of this as somewhat of a multivariate akin to the steepest ascent idea. So we want to keep going in the direction where there's interest, right? We don't want the flat part of the surface. Unfortunately, if you're in a standard software in DOE and you want to do an augmentation of your design, you're really limited to options that focus on the design space and don't really take into account the response. Okay, so in this particular case, you can add centers, or even in the augment world, what you have are augmentation schemes in terms of D-optimal, alias optimal, which are fantastic and highly useful. But for our applications, we really want to we want to maybe sacrifice some of the statistical properties in exchange for giving me more points that are associated with some of these very interesting areas where I see very large gradients in the response. And that, as it turns out, is what these autonomous systems are characterized by. So if we're looking at testing these systems, that is one of the largest challenges. And I'm working with the DoD on this, and we kind of have our top challenges for testing autonomous systems. You know, the biggest one is, how do we test autonomous aircraft? You know, we need to range the size of Arizona and Utah together to have enough safety, right? But the second one is how do we test where we have these, what we call boundaries, where we just have these steep drop-offs. So maybe to kind of get more into this, we can talk about the idea here of a gap filling design. So this is maybe an extreme example. So a space filling design here would have no holes, right? But here we've got a hole in the center and then one in the northwest. So it would sure be nice if I were able to add another 400 points that would fill these holes in, right? I don't need more up here in the northeast. I need them in the center and then this particular part of the northwest. Now, right now, the current option is to add some more space filling points. And if I do that, those are the blue ones. So I've got 400 blue points that are added, which looks like I did get some points where I need it. But if you kind of take the coloring off, you can see I'm still a bit sparse, right, in those areas. So what we decided to do is we needed to really focus those 400 points where they were needed most. So we came up with this idea of a gap filling design, and this is an add-in that we created in JUMP, which I'm absolutely happy to share with you all, both in the gap filling world and what we're going to talk about in the adaptive sampling. But the point being, you can see the blue ones here now are these gap filling design points, and they all are kind of where the holes are, right? So we haven't wasted any of them by replicating points where we're pretty dense. We've really put a lot in here. So we've kind of concentrated them. And then now when I look at that with the shading off, it kind of looks like it's a real space filling design where I have pretty much uniform, you know, peanut butter spread across the entire design space from -1 to +1. So the question is, how exactly do we do this? We do it by just starting out with our original points, and then we just, if you want to add, say, 400 more points, we add 4 times that, or 1,600 or 2,000 points. And then we're going to evaluate each one for how close they are to the existing points. So we can say, if you're an existing point, I'm going to give you a response value of 1. And if you're a new point, you're going to get 0. And then we do a nearest neighbors example or a algorithm. And then we're able to evaluate, well, how close am I? So for example, if I'm down here in the very center of this design, if I look at the 10 closest points or the 10 nearest neighbors, they all are 0, right? Different from that is, this blue one here, it's got a mixture of a lot of reds and blues. So our idea is when we come up with this model, anything that has a very low predicted value is going to be in a sparse area. So what we do is then we'll just sort on the predicted values, and we're going to take the very lowest predicted values, and those will represent the sparsest areas of the design space. So as it turns out, this is how that model worked. So the deeper blue it is, the more far away it is from the ones, which are the existing points. And you can see how we fill in these guys right here. That's neat, but what happens if you only do it once, it kind of overemphasizes the biggest gap there. So we like to do it maybe up to 10 times. So we just do if you want 400 points, we're going to give you 40 the first time, and then just keep adding along the way. So that iterative process really ends up helping. So we've already seen this helped some of our customers in practice. We have a friend who works at a company that makes engineered lumber. And this is an example right here. The engineered, like this is OSB here, which is the oriented strand board, kind of that plywood that has bits and pieces in it, which is enormously helpful for us as a world, because it's very green, because we can use all parts of the tree. But it's all held together by a resin, and that resin is a formulation problem. Some of you are familiar with the mixture models. So it's a very complex mixture model, meaning lots of ingredients as well as process variables in there. So very high dimension, and we kind of figured out that we could find a potential improvement in our process. And in fact, it was the best resin they ever made by using this gap filling idea. So in other words, it's pretty easy. If you only have 2 or 3 components, it's easy to see where your holes are, right? But if you have 20 different ingredients that go into something, that's very difficult to visualize. So that's why we are able to come up with these alternatives. And this is an email I just got from Dan last week, and I'll read it verbatim. It says, "We found some other interesting properties that resulted in breaking paradigms that chemists had held sacred for decades. So the design space expanded into areas that we'd never tried before. This is where the gap exploration tool becomes even more important. We now have better resins than the ones that broke a 3-decade drought," which, by the way, they broke that drought by using the mixture models and design of experiments, because this company had never heard of any statistical approach to testing. They just did it because they're clever chemists and they knew process knowledge. And the chemists haven't exactly embraced the fact that we dunked on them on their home court. So this is kind of a good point too, that, it's great when we in the design of experiments world have some data and can start seeing things and understanding the process is fabulous. And in fact, learn more than they even may know. But I would recommend that we work together with the subject matter experts and the chemists rather than maybe apart, but that doesn't always happen. In fact, we're working with a formulation on a new propellant for the Department of Defense, and the chemist there is absolutely enamored with our mixture model and DOE methods. In fact, we gave him an 80-run design, and his comment was, "I feel like I'm looking at the Mona Lisa." So he embraced our DOE versus these chemists were a little bit threatened, shall we say. But anyway, on to the main event here. What we're trying to do is talk about these autonomous systems So where we're changing, this gap, by the way, has nothing to do with the responses. So now we're transitioning a little bit. And now we're going to take a look at how have I been doing in terms of the responses. So where we're focusing on is these boundary conditions, okay? So maybe the best way to look at that is an example here. So this is a classic example called the Voronoi plates, but I'll just kind of cast it into a autonomous system example. So let's consider the Cybertruck or a electric vehicle that's trying to do a merge, as Doug mentioned at the outset, right? So we're trying to do a merge, and let's say there's two independent variables of interest. One is your speed of the car, and the other is the traffic density. Okay, so if we look at maybe this axis is our speed and this axis as the density, we can see down here in the Southwest that, you know, there's not much probability. I mean, we think of the response here will be the probability of an accident, right? So not much probability at low speed, low density. High density, medium speed, yeah, we got, you know, let's say it's a scale of 0 to 10. So we got, you know, 80% chances here. And then the worst is this area up here where you have lots of density and you know, pretty high speed. But down here, we can deal with the lower densities and speed. So anyway, you can see that there are these boundaries, right? So we kind of got this kind of spider looking thing here that are the boundaries. And that's where we really need to test, right? So our software, we really don't need to do a lot of tests down in the extreme southwest corner or northeast or southeast or northwest, right? We got that figured out pretty well. What we really need to do is characterize. So is it at 37.1 miles per hour with a traffic density of 50% that all of a sudden we go from no probability of a collision to an 80%? So where is that exactly? So that's where I need to figure out how I can sample there. And a lot of these things need to be done like near real time. So you're doing a computer simulation that you need to update it near real time. So here's a representation of our algorithm. The asterisks that you can see here are where we're going to put our new points. So you can see there's no asterisks here or here or here. So using our boundary explorer, we call it, we'll put those right there. So that's the idea of what we'll call adaptive sampling. So where did this idea come from? Well, I was working with Johns Hopkins Applied Physics Lab, and they have a very elaborate algorithm that does the same thing. And we started looking into it, and we're like, you know, we could actually use some off-the-shelf software product and come close. Because the problem with the Johns Hopkins solution is it's not very portable. So you have to have like a $20 million test program, and then you're going to go, you know, connect your system up at in Aberdeen, Maryland and whatnot. But we wanted to give it to some of our test teams that didn't have quite those luxuries. So we started thinking, you know, Jump Pro itself has a lot of AI, ML, artificial intelligence, machine learning apps that we can use and just write a script to kind of do this. And that's what we did. Here is the result of it. We created this add-in, and what we'll do is we'll kind of walk through how we add those extra points at the boundary. So the interface is quite simple in that you just go ahead and tell me what are your input variables and what are your input variables down here, and then your responses of interest. And we do have a couple of different options that we'll talk through here in a moment. So the first idea is we know in our world that these complex systems are driven by more than two factors, right? So often we'll have 50 to 100 or even more input factors, of which we know the sparsity of effects suggests that not all will be statistically significant. So we try to help ourselves out on the first pass in saying, okay, who is important in this game? If we're focusing in on the boundary areas with the response, well, who's responsible for that? So we do a screening, so using the predictor screening that's available in regular Jump even, and figure out that, okay, this particular one, it's the speed as well as the traffic density, and then we just threw in a noise variable, and sure enough, the noise variable didn't show up in terms of looking at our portion of variability explained. Now, you can manually choose what percent I want for that. So that's the first step. The next step is now let's kind of classify our points. Do we think they are boundary points, or are they in kind of the flat surface? So we go back to this k nearest neighbor idea, which is very well named. And if I'm looking at this point right here in the center of this purple circle, I look at its 5 or 6 nearest neighbors, and then I kind of see that, you know what, I've got, 3 of them that are 2s, and then 2 of them that are 8s. So I see a lot of variability there. Contrary to if I were to put that purple circle down here, all of them would have 2 as their response, and we'd know that that was not of interest. So we start kind of, each point has an evaluation of the 5 nearest neighbors. And then we try to say, are you very homogeneous, or are you non-homogeneous in that? And then we can dial in 5 nearest neighbors, 10 nearest neighbors. We find that 5 is sufficient for that. So not getting too much into the weeds here, but if I just happen to take a look at this particular row, I see that my response is 2. And then if I look at the 5 nearest rows to that and look at their responses, I can see that I've got 3 of them that are 2s and 2 that are 8. And then I have a standard deviation of that. And then I say, well, how far is the average distance from that? And if I use these 2, the standard deviation and the mean distance, I have what we'll call an information metric. Now, if I look at the bottom 2 rows here, I'll see that every one has a 2 for its response. So there's no standard deviation between there. So I'm pretty much assured that that's not likely going to be a boundary point. So that's kind of the philosophy that we're using. So once we have all of these, every point gets this information metric, and then we fit it to a normal 3 mixture, whereas the first is going to be the low probability of boundary, and then the second will be the medium, and then the third will be the high probability that we have a boundary point there. So now we've classified each point as whether it's a low or a high probability of being a boundary. And then from there, we can kind of color those points in. We can see right here, we've got low, medium, and high. And it seems like we did a pretty decent job based on what we remember from that Voronoi plate. So we also can do this with a non-contingent or a nominal response or categorical. And then the idea there is if I am all the same, like all of the responses is a C, then that's a low probability. If there's one that's off, then that's a medium. And if there's more than one, then we'll call that a high probability that we have a lot of variability going on there. We could also use an unlikability metric that's developed in 2011, but we just stick with the basic there. So now that I've got what we call our potential high probability boundary points, then what I do is I find the neighbor to that. So I looked at the 5 nearest neighbors. So of those 5, which one of you is most different from me? And I'm going to call you my boundary pair. And then I connect you, and then I just take the average or the midpoint of that, and that's where I'm going to put a new point. So the midpoint between the boundary point and then the nearest neighbor point, that's going to be where I'm going to generate a new point. So that's the midpoint algorithm. And you can see, we can say, you can check to say, do you want to do the midpoint? And you got that. And as it turns out, we find the midpoint is enormously, is the best method for finding that boundary. But we also have another method that we do as well, is once I find the particular boundary points that are high or medium, I'm going to go ahead and just put a random normal from like jittering kind of a thing. So I'm going to take that point and I'm going to move, and then I'm going to put another one, generate a new point close to it, not on it, but close to it from a random normal with a standard deviation of 0.075, which is very tunable. You may not want that. You may want to put them closer in. And that's what those red points are. That's called the perturbation method. So take the point and then add something close to it. And what we do is if it's a high probability of it's a boundary point, we add 2 perturbation points. And if it's medium, we just put in 1. And then the last way we do it is with the random forest, where we do it exactly like the gap filling idea, but we do it across all of the responses. So what we're going to do is we're going to kind of smatter in a whole bunch of new potential points from space filling. And then we're going to say, if you are a perturbation point or a midpoint, we are going to give you a value, and then we're going to use random forest to get whatever's closest to those perturbation points. And the midpoints, we're going to go ahead and score those with the random forest, which again will be a nice nice option for us to generate points outside of those. And then that's kind of what this random forest looks like. And then this is everything all at once. So the green ones are the random forest, which you can kind of see is sort of in the middle of the blue, which is really following that boundary quite nicely. And then we have the red ones, which are the perturbation has kind of gotten, probably need to tune that in a little bit, maybe bring it into 0.05 or something, but that's kind of how we do this. And then this is what it looks like, kind of a thing on the surface. And then lastly, there's a couple other options is we could add some gap filling runs, or maybe we want to look at the extrema, right? So go ahead and give me 4 points near the absolute maximum response, and then 4 at the absolute minimum, or whatever we'd like to do there. And then here is just one last example in terms of this Michalowicz two-dimensional guy. We can see that it really is just a regular square, except for there's a trench going in both directions. So we would really like to put more points in the trench. So here is what our doing 2 iterations of our boundary explorer has done for us. Is you can see that we're really kind of working in the trench, apart from these guys over here, these 8 points that I get at the absolute max. So to kind of see that dynamically, we can kind of see right now, I'm looking at the midpoint guys that are in there. And then, so if I added, I want 200 more points, you can see they're all in that trench there, that I'm not putting any on the very flat surface of that Michalowicz. So here, those are the perturbation method ones. And then lastly, we'll take a look here at the random forest versions. So anyway, that is what I wanted to share with you. Very exciting. We found many uses for it. A lot of excitement out there in the DoD circles that we now have a way to incorporate some of the responses. So these gap filling design is going to be an improvement over the space filling when you need to target special areas. Adaptive sampling is critical for large-scale simulation, and we really have found that it has been a lifesaver in terms of the run budget, in terms of the development time. Key point, DOE is not just for physical systems, enormously useful for both the Monte Carlo simulation stochastic world, where you do it almost similar to the way that you would do it for physical systems. But even when you don't have any noise in there, there's a different method or different path that we can go and exploit. And that's those space filling designs that we use. So we know that there's a lot of complexity in there, and think sequentially. So that hasn't gone away. That's still quite in fashion, even with the computer simulation and all the power that's out there. So when you add more tests, it is very helpful to put them in the most desired location. And lastly, the enabler to all this is the artificial intelligence and machine learning world here. So that AI ML does have a connection with DOE. In fact, I think one of our early work, Doug, was when you and George and I did that article with using these decision trees in CART for a complement to your regular DOE tools to understand. And every time I run a DOE, I do use those decision trees and regression trees to see what's going on.
Yeah, Jim, I'm glad you brought that up, because I always think of that work that we did in the paper as really one of the first examples of using those kinds of methods, coupled with more traditional experimental design techniques. And I thought that was kind of a revolutionary idea at the time. I really did. I thought that was quite unique
and very useful too. It's like,
oh,
wow.
Yeah. Well, you touched on a number of things in this talk that I've found really interesting, and I want to point out to people taking the course that in our course we do talk about computer experiments. There's some material there, and there's probably even a little bit more material in the textbook in chapter 11 that maybe we don't talk about as much in the course, but there is some reading material and some references there that people taking the course would maybe find useful, because the use of computer experiments in the engineering and science world has just grown by leaps and bounds over the last 5 or 10 years, and that's going to continue. And then the other topic that you touched on that's also mentioned in the course is the idea of mixture experiments. And again, we probably don't do nearly as much with mixture experiments in the course as we could. There is material again in the textbook, chapter 11 in the book, on mixture experiments, and mixture experiments come up a lot. They come up a lot. And sometimes people don't even recognize that the experiment they have is a mixture experiment. And I've got a real live example of that right now with one of the students that is taking my experimental design class here at ASU. He's doing a term project, and he's doing a term project involving plasma etching. Okay, and so he turned in the proposal for his project, and he says, well, we're gonna vary the flow rate of this gas and the flow rate of this gas and the flow rate of this gas, and we're going to see and we're going to change the temperature, the temperature in the chamber, and we're gonna change the RF power that's being applied to the anode cathode gap, and we're going to see what all these factors have to do with the etch rate on this material that's in the chamber. And so he's going to treat all of these factors as if they're independently adjustable. And I said, do you think that the chamber pressure has any effect on etch? He says, oh yeah. I said, well, what do we know about flow rates of these gases? Well, they affect the partial pressure. And isn't it true that the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C affects the total chamber pressure? And he starts thinking about this, and he says, yeah, maybe you're right. So guess what? These three gas flow rates need to be treated as partial pressures, and they're not independently adjustable if you want to hold the total chamber pressure constant, which you probably do. And oh, by the way, you can independently adjust the RF power, and you can independently adjust the temperature. So guess what? You have an experiment with 3 mixture components and 2 process variables. and now to give the guy credit, once he figured that out, he jumped right on it. And figured out how to set up the appropriate experiment, and you can do that in JUMP, of course, without any difficulty, which I use in my class. And I can't tell you the number of times I've run into this situation in my consulting work, where people have mixture experiments but don't realize it. And if you treat mixture components as if they're independently adjustable, things very often fall apart. You don't get good answers. And I suspect you've run into that too.
Absolutely, yeah. So we're probably at least a third of our work is in formulation, because we do a lot of R&D, of course, on the biopharma world. So a lot of that is the mixture. But to your point, a lot of folks don't get that there's those dependencies that go on there. So you can always come up with, they have to sum to 1 and these, but there is already some science that's been plowed by John Cornell, right?
Yes.
doing some great work pioneering that whole world, which to this day, there's still a lot of statistical challenges, particularly when you have complex, like I was telling you, the propellant formulation, we have 28 constraints beyond the thou shalt, so the ratio of A to B has to be less than 0.2, A1 plus B1. So you put all those in there. And now you're really looking at some not great power and metrics that we're typically associated with, right? So
some mixture experiments have lots of components. I could remember talking to Greg People,
yes,
who did a lot of work in the mixture area, and he worked for Pacific Northwest Labs for most of his career, and he worked a lot on formulating the glass mixtures that are used for containment of nuclear waste. They take the nuclear waste and they put it in a glass container and they bury it where the sun doesn't shine for 100 years. And we hope that everything is okay. But he said he very often had mixture experiments with 30 and 40 components. And that's just a phenomenal problem. I've worked with people that had a fairly large number of components and lots of constraints, but nothing like that. I mean, that's just truly amazing. And the more complicated you make the experiment, the more crucial it is that you have good experimental design strategy to solve these problems, because they are. If you don't, you just simply don't get very good results.
And very true. And we have found, of course, the problem, the AI ML world is nice, and predictive analytics is nice because often you have a lot of data and you can do your partitioning of your training set and your validation. But in DOE, often we're extraordinarily resource constrained. So what do you do then when you've only got 20 mixtures? Well, Phil Ramsey and Chris Gottwald, they're doing some really nice work that we're using on SVEM, self-validating ensemble models, where you use you're using your 20 observations, and then you're using those both as training and validation, which seems crazy. But when you start doing some of the neat math tricks that they do in there, it actually works out, and you can kind of find that signals or isolate the signals. Kind of a thing. So that's why I say there's very much more research needed in that area to understand these complex mixture models. But it certainly beats the alternative of just kind of guessing, like the chemists at the lumberyard or the engineer. They just thought what was best. But now, if we have a method to the madness, in DOE really is a force multiplier. So.
Well, there are so many problems in the mixture. Just I know we're probably going off a lot on mixtures here, but there's so many problems in the mixture world that really deserve a lot more work. And the experiments with large numbers of components is one. Hard to change factors is another.
Oh, right.
Yeah. In integrating split plot type thinking into mixture experiments is a difficult issue. I had a student a few years ago whose doctoral dissertation was on mixture process experiments with hard to change factors, and he did some really nice work on this. But did we ever come up with a commercially viable algorithm? I don't really think so. We ended up using genetic algorithms to create some of the designs that we did, but there's still a great deal of work to do in that area. And
but isn't that fantastic that you, as a research professor, are researching things that, no kidding, are going to the practitioner? I mean, we need this, right? I mean, there's a pull force here. It's not just doing research for research's sake. It's like, no, this is actually going to be implemented.
Well, a lot of some of my current research is sponsored by the DoD. And as you know, it's involved with operational testing, and there's a world where new problems come along every day, And probably one of the biggest problems is it's difficult to do sequential experimentation because you have the equipment, you have the operators, and you have the facilities. Okay, and you've had to book that months in advance. And so you set up an operational test and you run through the test and you say, gee, we need to add more runs to this experiment, in order to really get the kind of results we want. And people look at you and say, the test resource management people look at you and say, well, yeah, you can have the range again in 6 months.
Right.
And
Yeah, no, I mean, that ultimately is why the sequential is I want to say dead on arrival, but in some sense, the DoD is not set up the right way for that because they just sign off, okay, your budget for testing is, $22 million. So tell me everything you're going to do with that $22 million. And you're not going to get your test and evaluation master plan signed if you say, well, we're going to use half of it and figure out what we learned. And then we'll use another quarter for this and things that you would do smartly, you can't really, because you have to have your test strategy laid out in its entirety.
And I kind of understand that because the facilities that you use for testing are limited.
Mm-hmm.
I mean, there's a long line of people that want to use Edwards Air Force Base. Okay, I understand that, and so you have your shot. And maybe you get to come back in 6 months. And then there's the equipment itself. You're with operational testing, you are looking at essentially an end stage system that we want to send, to the well, as an old Navy guy, I would say we want to send to the fleet. Okay.
Yeah.
And until you get through that operational test, it's kind of difficult to start making these things by the dozens or hundreds or whatever, and send them out. And you don't want to delay that another 6 months or a year because you need more operational test data. But on the other hand, you don't want to send stuff out there that isn't fully
right. It's
tested. I mean, it's
the error, the type 1, type 2 error there, right?
Yeah.
So,
and the example of this that I keep thinking of right now, that I harass my students about all the time, is Boeing's problem with the flight control system, the MCAS autopilot system on the 737 MAX. There's a system that was not properly operationally tested, and it was fielded way too soon. And up to date, they've only killed 375 people.
but they have a fix. So
let's hope they have a fix, and let's hope they know how to do the operational testing to make sure that the fix works.
Yeah, I'd have to believe the politics and the gravity of the situation suggests that a lot of people are looking at that data, and there's a great degree of certainty that they have it.
Yeah, let's hope. But I always tell the students in my experimental design class here that this is why I'm not very gentle with you in this class. Is there's certain things that engineers need to learn how to do. And, bad doctors kill patients one at a time. Bad engineers kill people tens, dozens, hundreds at a time. And, I don't want to have any responsibility for that. That's okay. So maybe we should take a look at questions. We've only got a few minutes left here. We've got about 10 minutes left. So let's see what we've got in the way of questions. I think we've had a couple come in. Okay. And Megan is getting them blasted up on the screen for us pretty soon here. Okay. Okay. Here's Jim, I'm just going to go ahead and read this.
Okay.
Okay. And then you and I can talk about it. So I've recently completed the whole DOE specialization and am now trying to apply it to my work as an experiments engineer. I'm trying to investigate whether the frequency of fuel change affects fungus growth in the fuel tanks of aircraft. Oh, interesting. So an experiment was devised. The whole population of airplanes was split into two. Half of the airplanes was called reference population and half of the airplanes experiment population. At the start of the experiment, both populations performed daily fuel changes, a process in which the fuel from the tanks is emptied completely and new one is being filled in. Okay. At time t equal to 0, a fungus test was performed on both populations, and that the experiment population switched to weekly fuel changes. And after 6 months, 1 to 6 months, another fungus test was performed in both populations. Each aircraft had 3 fuel tanks, 1 in each wing and 1 in the belly. Okay, so the factors of frequency of fuel change, categorically 2 levels, tail number of the aircraft, categorical random variable. I would think of that more as a blocking factor. I don't know.
Sure, random block. Yep.
Yeah. And then fuel tank categorical are just 3 repetitions. The response amount of fungus per liter of fuel. In addition, the response is extremely non-normal. Lots of zeros, some mid numbers and few high numbers. Even log x+1 transform doesn't make it normal. You know, this might be a place where some sort of generalized linear model might be appropriate. Something you know, either a Poisson response distribution or something like that. I'm thinking.
Sure, and there's even, you have the flexibility of 0 inflated distributions.
Yeah.
Like that
Yeah,
too.
yeah.
So,
And the thing is, in JUMP you can fit Poisson regression models,
right.
and
Yep.
so that would be a possibility. So okay, so I've tried block design, block by plane number. I think blocking by aircraft is reasonable. Only the experiment population is used in this design, as it needs to be symmetric. So reference population data is lost. Okay. Nested design, plane number nested to frequency of fuel changes. Not sure about that.
Yeah.
Versus t equals 0, measurement of experimental population, and versus reference population at t equals 6 months in both. Non-parametric exact test, ANOVA, rental, plane number being a random variable, several more. All of them give different results, different p-values. Since the data is so severely skewed, tried transforming 0 to 1. Yeah, okay.
That's what I was thinking, was looking at binary just for that first step, kind of the exploratory data analysis.
Yep. And then using, and if you do that, of course, you use a generalized linear model, you know, a binomial log link, you know, type stuff. What would you recommend? Well, in a sense, this is kind of like a clinical trial of
absolutely.
Yeah, it's like, and so some of the literature on clinical trials might be worth looking into. I think that's maybe a place I would start, because in a sense, you've got a patient that's being treated. That's your experiment airplane, and then you've got you know, the untreated customers, and so you can sort of look at you know, look at it as a clinical trial. I think maybe looking at the data from a binomial viewpoint as a starting point is a good possibility. It's a good possibility. If it really is count data, though, there's always the possibility of the Poisson. So there's a couple of ways to think about that.
Or for that matter, just start out and just use the platform to fit the distribution. You know, if you're using JUMP, it has, you know, 25 or so, and it's, you know, tell you which one is the best. And some of those you kind of have to temper and say, all right, I don't need the inverse log gamma, you know, 0 inflated thing.
Right. Yeah. You
close enough to that is the Weibull with beta equal, you know, 1.3. So
right, but you can be a little selective about how you do that. But I'd certainly look into that possibility,
because they rack and stack them, and you can pick one that is close to something that is understandable, because you got to sell this too, right? very important that we can have all these fancy methods, but if they fall dead to the ear of your leadership, then what have you ultimately done, right?
Yeah. So this may be a follow-on question for you. Is this a software tool that is open source? And I wonder if is that referring to the software tools that you were talking about in your presentation?
Yeah,
and
so
I think it is.
yeah, so certainly in terms of the gap filling and the adaptive sampling, that is open source, in that I'm happy to provide that to you as an add-in to Jump Pro. So Jump Pro is anything but open source. So you'll need that, not just Jump, but Jump Pro. And to be honest, Doug, you mentioned working with the DoD. This research was sponsored by the STAT COE. And the follow-on for us was, in fact, to put this into an R-Shiny app, but we just haven't been funded to do that. In that case, it would be completely open source, and that's kind of where I wish things would go more so.
Yeah, but on the other hand, Jump is easy. You can get trial versions of Jump. And if and I've always told people that if you're doing design experiments and you're not using something like Jump or Design Expert or Minitab, you are camping out. You're just camping out.
You're right, and it is sad that people can't do that return on investment analysis to say that I got it, that R is free and R can do this. But the amount of time that it's going to take versus the point and click to have these become random blocks in the previous discussion that we were talking about, and then choose that I want to use, a logit transform with the binomial link and whatnot. That is countless hours of productivity.
Yeah, and if you bill out engineering time at $100 or $200 an hour, just think about how much that cost you.
Absolutely. So
okay, so Jim, we're at the end of time here, and I want to thank you very much for spending this time with us. This concludes today's session. I really appreciate everybody that logged in today. Our next Fireside Chat is in January of 2022. It's Wednesday, January 12th. And information on that is going to be out soon. And meanwhile, have a great rest of the holiday season. Relax, enjoy yourself, stay safe, and we'll see everybody in the new year.